Hello, everybody. First of all, I would like to thank AAPG, Petroleum Structure and Geomechanics Division, the invitation to speak to you today, especially Dave Hada, Molly Turco, and Caleb Pollack, who helped me to coordinate this presentation. It's a pleasure to speak to you today, and I'm going to talk about a very interesting topic that is also novel and is related to the quantification of spatial arrangement of fractures using a technique called normalized correlation count. The work presented today was compiled by me, but it is part of the efforts of many researchers from the Bureau of Economic Geology that work together with me in the frac consumption group, and that allowed me to share with you part of their data and publish articles as well. And I'd like to thank them for the support and also thank Petrobras for sponsoring my research since the beginning. So this is the agenda we are going to follow today. I will start explaining my view on what is spatial arrangement in the realm of fractured reservoirs, and then we will talk about the available methods that quantify spatial arrangement of fractures, more focused on the correlation integral technique, from which the normalized correlation count, the focus of the talk today, derives from. And I will explain how the technique works, and then I will show you several examples of applications in syntactic data and also in real data from one dimension and also in two dimensions. And in the end, I will show some practical applications for industry in a very interesting case study from the Frontier Formation published by Lee et al. 2018 that used normalized correlation count in subsurface. So what is spatial arrangement? The prediction of fractures in subsurface is one of the most challenging problems in geoscience. And a big part of the problem is related to being able to predict fracture distribution and arrangement in the reservoirs. And some authors depict fracture distribution in subsurface as being regularly spaced along bed thickness, and this is what is considered in many subsurface models. But in reality, fractures can have several types of arrangements. That includes being regularly spaced, also randomly distributed, or clustered, like this figure on the bottom, forming fracture corridors that can be very important features causing heterogeneities for fluid flow in reservoirs. And the reason why different types of fracture arrangement arises is still an open question, and the causes can be many, but a crucial part of the work to understand this process is being able to quantify different types of arrangements. And this is the first step to understand how these different arrangements arise, ability to predict it for reservoirs in subsurface. And what is the definition of spatial arrangement? A more useful concept than spacing that just concerns to the average distance between adjacent fractures and cannot distinguish between more complex patterns is the concept of spatial arrangement. Spatial arrangement is the property possessed by an array that is defined by the pattern of fracture locations. What I mean in spatial arrangement is spacing plus position. And for example, a typical practice for assessing the fracture abundance is to measure fracture spacing, but many fractures in subsurface are not regularly spaced, turning the average spacing metric not adequate. We can see why in this figure here. The same mean spacing can yield different fracture organizations or arrangements. They can range from being regularly spaced to being randomly located, or sometimes forming clusters. Techniques that consider spatial arrangements can identify these more complex patterns of fractures and give us a better characterization of the fracture pattern. And how can we quantify the spatial arrangements of fractures? Well, luckily there is a good amount of literature in this subject and many very interesting techniques that help us to quantify spatial arrangement of fractures. Speaking about some of them, the coefficient of variation is an excellent technique that provides a good idea of how organized the fractures are using the standard deviations and mean of the spacings. Variograms are also it's also a well-known technique in geostatistics that has also been applied to analyze fracture spatial arrangement. Specifically in this article, shows it being applied in fracture trace maps in 2 dimensions. And the Cooper's method, very interesting, and it measures how much fracture pattern departs from a uniform arrangement by measuring this d distances that is from the uniform arrangement line that is plotting on the middle of the graph. And the cumulative frequency plots also are very commonly used and describe behavior of fracture sizes or spacings. And the slope is usually a very important parameter in this graph. Ripley's K function is a geostatistical technique based on measuring distances applied on fractures by a fellow UT student. His paper should come out soon. And on the bottom, we have some other techniques that have one thing. They all derive from the physics and the fractal literature. And these are the correlation integral, the box counting method, and the lacunarity method. They are able to estimate the fractal dimension of a fracture arrangement. And the box counting does that by counting the number of boxes that have fractures in it with varying sizes. The lacunarity does that by estimating the varying sizes of non-fractured areas along the skyline. And the correlation integral does a similar job, but by counting the distances between the fractures. And today I'm going to focus on the correlation integral method because that's from where the normalized correlation count derives from, and I want to show you how it works. So if you want to focus on to dive into the method, you can start by reading this literature here. The first one here is from Henschel and Procaccia, 1983. It is not a geology paper, it's actually a physics paper that gives you like the roots from where the technique started on measuring. Actually, it was developed to measure fractal dimension of features in the physics, in physics research, and coming from all the way back from the works from Mandelbrot in the 60s that started to actually study fractals. And the 3 papers on the bottom here are actually applications of the correlation integral technique on fractures. Born et al. Uses that to calculate fractal dimensions of fractures, fracture traces. And Myret et al. Actually does really very good improvements of the technique and shows how the normalized correlation count is done in this paper here. That will be the most important for the talk today. And also Sanderson and Peacock does a very good review on all these techniques that are available to characterize the spatial arrangement of fractures in scan lines, and it's also a very good paper. And so talking about the technique itself, it is based on this equation here that we see. We have as input a number of fractures, the length scale that we're going to analyze, the distances between fractures, and also in there we have this H that it stands for the have side step function that returns 0 if negative and 1 if positive. So what that allows you to do, that it actually counts the number of fracture pairs within a distance, and that's what the correlation integral will do. It will tell you the amount of fracture pairs that is within a distance. And I'm going to show you how to calculate that simply in a simplified way using this scan line on the right. So here on the right, you have this black line that is the scan line trace, and you have many of 3 fractures that are in red here. So if you calculate the distances between the fractures, you will have distance 1, 2, that is between the fracture 1 and fracture 2, distance 1, 3 between fracture 1 and fracture 3, and distance 2, 3, right? And what you do to calculate the correlation integral is that you need to choose a length scale, that is this small length here, and then you're going to ask your scan line, how many distances are smaller than my length scale lambda 1? And in this case here, none of the distances are smaller, so your correlation integral will be 0. But if you go ahead and choose a longer length scale, and then you're going to see that in this case, D12 is smaller than lambda 2. Then 1/3 of your distances are going to be smaller than lambda 2. So that makes correlation integral a third, 0.33. And just to close here, if you have the longest length scale here that is bigger than all the distances that you have between the fractures, your correlation integral will be 1. So this is a very simplified way of thinking about the method, but you can imagine that instead of 3 fractures, if you have hundreds or thousands of fractures, this will be a very computational demanding method, and it could be very complex too. So from the correlation integral, we can also manipulate the correlation integral results into 3 more values. The correlation count, that will be basically the difference between 2 values of correlation integral for different length scales. This is like a delta. The expected correlation count, that is calculated by this analytical formula here, that uses the length of the scan line as input, and this will give you the expected correlation count for a random arrangement, as if the fracture were randomly arranged in your scan line. This will give you the correlation count for that type of arrangement. And just to finalize, we can use the equation 3 to calculate the actual normalized correlation count. What is actually a ratio? This is actually the ratio of your input data, the correlation count of your input data, with the expected correlation count for a random arrangement. And that tells you that if NCC is bigger than 1, you have length scales that are more frequent than random or clustered. And if NCC is less than 1, you have length scales that are less frequent than random. And as this plot on the right tells you, you will have always a plot of, usually to analyze the NCC results, you will have a plot of the length scale on the x-axis and NCC on the y-axis. And then you'll have the expected correlation count here plotting as 1, right? Because it's the random one, as if you would divide here random by random will be 1. And you would have your resulting analysis here crossing this graph. If you have it plotting here on the top, it's going to be more frequent than random for these length scales. And on the bottom, it's going to be less frequent than random. I'm going to show some examples. And on the top of that, we also have these charts that are calibrated with synthetic data and also real data, and that give you direction on how to, on the resulting data that you might have on your data, on your input data. So basically, you will have this NCC pattern coming from your data, and then you can use this type of chart to help you interpret what that means. So For example, if you have this kind of pattern in your NCC curve, plotting all along close to NCC1, that gives you the information that your pattern is indistinguishable from random, because it is never going to it's never departing from one, right? If you have, for example, now in logarithmic graduations, a very constant slope that could be adjusted by a power law. Of course, in logarithmic graduations, it's going to be a power law is going to be aligned, right? And where this line touches the NCC1 right here, it is going to give you the cluster width. And if you look at the same, at this fractal cluster, for example, in a linear graduation, you could see some of these patterns also that is kind of wavy. And this wave, it tells you that you have a repeating pattern of lengths. And this first peak here will tell you the cluster spacing. So these are very easy charts to use during your interpretation of your data, and can help you to identify what kind of arrangements you have just by looking at it, and really useful and helpful. And also to be able to separate what is considered a random arrangement from what is not random, we use randomizations, multiple randomizations of your input data using Monte Carlo simulations. We often do it more than 100 times. And what we have from these randomizations is distribution of correlation count, normalized correlation count for each length scale, and using the confidence limits, the distribution, the P97.5 and the P2.5, giving a 95% of confidence here on the middle. You will be able to plot these upper and lower limits of the random arrangement. And that means that if you have a pattern plotting on the top of this upper limit here, you can say that it is clustered with 95% of confidence, that it is distinguished from a random arrangement. So it's a stronger clustering that a random arrangement would ever be able to give you. So let's jump to some results. This is the Marble Falls formation from Pennsylvania of Central Texas. These are some carbonates from Pennsylvania age. From this paper from Marriott et al., he published this scan line that it was done here in this location here, crossing some of these veins going east, northwest direction. You can see here this fracture intensity plot. We have at least two big clusters here, one on the beginning of the scan line, and another one here that also have a distinguished fracture intensity very high. And the plot in the NCC the NCC versus length scale here, you can see that the blue curve from the input data plots way above from the random arrangement envelope here, telling you that this pattern is very clustered. And if you take a look on the chart that it tells you what a fractal cluster is, it is very similar to this one. So it's a constant slope, and it in fact can be adjusted by a power law. And that will tell you here, just when you get to NCC 1, actually the cluster width that you see in your data. And you can see that this is about 8 meters here, the cluster width. And in the linear plot, you can also take some information of the cluster spacing. That's where the NCC curve comes back again. And this high value here will tell you that in about 18 meters, you will find the cluster spacing. So center to center here, these two clusters are spaced in about 18 meters. So this technique is useful to give you a quantification of the clustering of fractures and how these fractures are arranged. The internal organization of these fractures are fractal, and that tells you these very important characteristics of your fracture arrangement. This is another example from the organic carbonates in the Cretaceous of France. We went to this area and did a scan line here in this location, crossing this main fault plane here. So we went from the Rose Rock, passing through the damage zone and going to the Rose Rock again and crossing the main fault plane. And we identified two main fracture sets, one going northeast, and another one going northwest. The northeast is the most present one, the most frequent one. And we can see here on the right a figure of these opening mode fractures. These are northeast fractures, very cemented by calcite. And the host rock here is grindstone that is also very cemented. You can see here in the first stick plot, this is the whole scan line that is composed of 109 fractures. And we were able to separate that into fracture sets. In the middle, you can see the scan line just considering the northeast fractures. And in the bottom, scan line just considering the northwest striking fractures. These are both opening mode fractures and cemented also by calcite. The analysis with NCC for the northeast ones give us also a very strong clustering here, fractal clustering adjusted by a power law with a cluster width of about 1 meter, also very similar to the pattern seen in the chart. And if you look at the linear scale, the plot in linear scale, you are able to see this wavy pattern that goes all along. And the first one here will give you the cluster spacing at about 5 meters. So if you go back and look at the stick plot, you see that this cluster here has about 1 meter and that they are spaced in about 5 meters. So that's a perfect quantification of what's actually happening in your stick plot. And if you take a look on the northwest fractures, you'll see that you have this pattern that looks like a plateau that is also indicative of a clustered individual that is just above the confidence limits of random. And if you take a look on the spatial organization, the arrangement of inside this cluster just below a meter, that's the cluster width, right? A meter. If you take a look and look just very detailed on below that 1 meter, you're going to see that it has a very regularly spaced pattern, just like the chart shows. And if you zoom out and look at longer length scales, you see that this pattern also have a peak in here that is about 12 meters. And that will show you basically in summary that you have cluster that is 1 meter wide. Internal organization of these clusters have these regularly spaced fractures, but they are apart 12 meters. So yeah, that's basically the resulting analysis gives you a lot of quantitative information of your scan line. And another very interesting example is this scan line that we acquired in a quarry in Provence, also crossing the Amandier fault. These are also from the organic carbonates. It's a Cretaceous carbonates in South France. And these black parts here are the faults crossing also our scan line. And we basically crossed northwest fractures in there. Basically, the set that is most predominant is this one going almost northwest. And we analyzed this 264 fractures in this case. And the pattern returned to be totally indistinguishable from random. So we can see here on the bottom that we can actually see some clusters, right? Here and here and here. However, these clusters, they are not as strong as the other ones that I showed you. And they could be perfectly we are able to reproduce these clusters just by a random organization of the fractures along the same length of this scan line. So the fractal clusters and the distinguished clusters that plots all the way on the top of the confidence limits are stronger clustering and very different from this one. So that tells you also some information about the processes that are causing the clustering in your area and how distinguished these clusters are from the other area as well. What if the problem is in 2 dimensions? We have here this figure showing this drawn images and fracture traces interpretations from this pavement that is on the Marble Falls Formation, the same place that I showed you before, an example of a skyline, the Pennsylvania of the Central Texas. So this is depicting very different arrangement of fracture traces, right? You can go to the top here and see that in this place you have less density of fracture traces. And here on the middle, the fractures are just like packed, right? It's very intensely clustered. So what could we use to characterize the spatial arrangement of these fractures in 2D? We could use maybe variograms, but variograms don't tell you much about the internal organization of the clustering. It will just tell you about the spatial continuity, maybe of the densities, right? So what we started to do is to expand the use of normalized correlation count to 2 dimensions. And that's what I'm going to show you now, some results. Just before that, I would like to make a disclaimer that this is under development, and we're going to share some preliminary results in the following slides. So from the fracture traces, this is a more complex problem because fracture traces can have infinite positions along the trace. And if you want to use correlation integral to calculate the distance between one fracture trace to another, you can have many positions where you can choose that, right? And that's why we based on past references, past works of these authors here, referenced in here, we choose to use the midpoint of the fracture, the barycenter, to analyze the distribution of the barycenters of these fracture traces. And we know, obviously, that a complete analysis would take also a length analysis and orientation analysis. And this is going to be also done. But for now, I'd like to show you just the results using only the barycenters and what we can see just using the barycenters to analyze the spatial arrangement of these traces. And so using barycenters, the formulas are going to be the same. The technique is the same, but now instead of analyzing distances between fractures along the scan line, we're going to analyze distances between the barycenters in the area of study, right? In this case here, we have 1 point, and then the distances will be D1, for example, to the other barycenters, D1-2, D1-3, D1-4, and this is going to be compared to the length scale being analyzed, just like in 1D. And this was written in a Jupyter Python notebook by me, and I can input, the input is basically the XYs of the barycenters, and then you can run the algorithm, and will calculate the NCC curve for you. And we also have an analytical solution for this problem. And this is basically calculating the expected correlation count for the random arrangement of points in this circular area. And for that, we basically use the radius of the study area, the size of the length scale being analyzed, and this will give us the resulting expected value of correlation count. And this was a contribution of our fellow student, Mahmoud Shakiba. And also to calculate the confidence limits for a random arrangement of points in this circle, we take our input data, the same number of features, the same area of analysis, and we randomize it 100 times or 200 times, how many times you want, and we'll have the distribution of, we calculate obviously the correlation count for each time, and then you will have a distribution of correlation count for this random arrangement. And what you do is just plot the confidence limits as the P at 7.5 and the P 2.5 from that distribution. And that will give you a 95% of confidence that of that random distribution, right? And that's exactly what we did for this pattern here. And I'm going to show you now some synthetic data, and just to uh, uh, give you an illustration of how the technique is able to see different types of arrangements. So this one is it's a random arrangement of fracture barycenters. An example of a fracture trace map that would be constrained by this barycenter is this one, as you can see. And if you analyze this random arrangement of fracture barycenters, you would have an NCC plot that is plotting just inside the confidence limits of random arrangements, and that will give you information that this pattern here is indistinguishable from random. If you had a clustered arrangement of points like this one here that has about 50 meters, you can illustrate this arrangement of barycenters by having a fracture trace map that is much more packed here on this part than is here. It is commonly seen in fracture trace maps. So this kind of arrangement will give you a plateau like this one, and with the place where it touches the NCC one will give you the cluster size that is also about 50 meters. If you have, instead of those patterns, a more complex pattern, like a fractal arrangement of barycenters, of fracture barycenters, like the contour 2D pattern could give you, you would have example very densely clustered packed fractures along this clustered barycenters. And this will be an example of fracture traces that would be arranged fractally. And you would be able to see that through the barycenters by seeing this power law, this constant slope going towards NCC1, and the place where it touches NCC1 will give you the cluster size that is about 120 meters. And if you had a periodic arrangement or equidistant arrangement of fracture barycenters, that is actually the pattern that is in hexagonal jointing. For example, in columnar basalts, you would have the same kind of barycenter pattern. And this would yield a NCC pattern that is wavy, very unstable, giving you peaks and troughs just above and below the confidence limits, like a wavy pattern. And the first peak here will give you the individual spacing of 10 meters. So as a summary, we can say that both in linear scales and logarithmic scales, we have a pattern that could be identified just using barycenters of fractures, right? Like the random barycenters will always plot here on the middle of these confidence limits. If you have a clustered, non-fractal clusters, you would have this plateau, and we could get a cluster size here. And if you had a fractal arrangement of barycenters, you can have this slope, and you can get the cluster size by the intersection of this slope with the NCC one. And if you had a equidistance or periodic arrangement of barycenters, you could have the individual spacing here and this wavy pattern that goes all the way along. And now I would like to show you actually applications of this on real outcrop data. And we're going to see how much information we could get out of these outcrops by using the NCC and analyzing the barycenters. So this is a fracture trace on the Little Coal Creek in Wyoming. This is sandstone. These are sandstones from the Frontier Formation that was published in Lubbock, 1991. I digitized these maps and calculated the barycenters from these fractures. You can see the digitized maps in here, and from that we put the XY coordinates of the barycenters in the algorithm and analyze the NCC plots for that. You can see that in this case, the pattern plots within the confidence limits, and that gives you the information that these barycenters are randomly arranged, right? And you can see also in the linear scale that it is all the way within the confidence limits. We also analyzed the fractures in the drone images from the Pedernales State Park, from that Pennsylvanian carbonates that I showed you before. And from that fracture traces, we were able to calculate the barycenters of that. And these barycenters give us a completely distinct pattern that is fractally arranged, because you can see this constant slope on the logarithmic plot that can be adjusted by a power law. And this place here tells us the cluster size that is about 19 meters. And that's about the size that you're seeing there, 19 meters. That is about the size of this cluster here. If we go up to UK and take these beautiful images from the columnar basalts from Giant's Causeway, there are beautiful hexagonal joints, and well, we digitized some of these aerial maps, aerial images, and calculated the barycenter from these fractures too. And well, it turns out that the barycenters from these structures actually gives us a similar wavy pattern, right? With troughs and peaks going up and down from the confidence limits all the way through the length scales. And this first peak here will give you the individual spacing that is about 0.25 meters between each barycenter of these fractures. So this just is a nice example of how NCC is a powerful technique that could be also used, well, can be used very well to give you information in scan lines, and it's also possible to use it in 2D. And this is under development, and I am hopefully will have much more results to show you and share with you in the upcoming months. So I would like to close the talk now showing a practical application of the use of NCC in the industry. And these are this is a study done and published by Lee et al. 2018 of a study of fractal arrangement in image logs. So this map here is the map of the Great Green River Basin. And you can see here on the right side 3 wells. We are going to talk about two of them, basically only the RI4H and the SW1H well. So these are horizontal wells, and you can see here from the rows diagrams that they have this very predominant fracture sets that are going towards striking east-west, northeast, east-west. And they also analyzed here in 2 outcrops of the Frontier Formation. These are all drilled in the Frontier Formation, which is a Cretaceous sandstone from in the Wyoming state. And these 2 outcrops have pavements of the Frontier Formation, and they were also able to analyze the spatial arrangement in scan lines that were acquired in these outcrops. Here on the bottom, you see example of image log going through one of these wells, where you can see here some fractures. These are horizontal wells, so the fractures are here appearing as a very high angle features, and the bedding here as a low angle feature, as you can see. So the resulting analysis show you, let's start first with the RI4H well. So this is actually the highest gas flow capacity of the frontier formation. And you can see from this image log, the stick plot acquired from the image log, that there are many fracture clusters in here, and the normalized fracture intensity plot here, this is just showing you the intensity along the length of this scan line. It just show you here that you have a huge cluster here that is very densely packed, and a lot another smaller clusters here on the way through the end of the well. And the NCC analysis, the normalized collation count analysis, gives you this analysis showing you a very distinguished clustering that has also fractal behavior. And you can see here that it is plotting along the same slope, more or less the same slope, giving you information that is somehow fractally, internally fractally organized. And the other well, SW1H, had a high water production and an early breakthrough of water. And you can see here that it also have many clusters appearing through the well. And this huge cluster here appearing around 200 meters, that if you take a look in the fracture intensity log, you're gonna see that this cluster have about 120 meters. It's really wide, and the normalized collation count of this well gives you the information that these clusters are there, because it is distinguished here from random, and it's a very strong clustering, and that the size here is about 120 meters. So these are very interesting information that could be acquired using NCC in the subsurface. And although we cannot really directly link the presence of these clusters with this distinguished fluid flow behavior, like the high gas flow capacity and the early water breakthrough, we know that often clusters in subsurface can really have major impact in the fluid flow. And the analysis here shows that you have strong clustering and they are very wide. And this is certainly information that I would like to have for my subsurface analysis. So that's what NCC gives you. And just to close, this is my last slide. I would like to show also a different, a very interesting finding in this study, that they also did the NCC analysis for the outcrops in the frontier formation, but the analysis of spatial arrangements come out to be very different. The spatial arrangements for the fractures in the same formation, the frontier formation, for the same set, but only changing from subsurface to outcrop. In the outcrop, it turns out that the spatial arrangement is random, not clustered. And this is actually a red alert for us that sometimes use outcrops to as an analog to subsurface, because that tells you that some difference actually may arise from this difference from the subsurface to outcrop. And when you look also in the cement content of the fractures in outcrop, you see that they have a small amount of synkinematic cementation, of quartz synkinematic cementation, while the subsurface fractures that are clustered have a lot of bridges and higher amount of cement. And that gives you also the indication that probably the history, the burial history, the mechanical history, the temperature and the pressure were all different along these two locations. And that's why all the cement is also different. And that may have caused, along with many other variables, the difference in the spatial distribution of the fractures. So this is a very interesting finding that I would like to close my talk with that. And well, thank you all for listening, and I'll leave my mail address here for a minute, and with some other very interesting references that are using the method. And with that, I'll take and answer any questions that you might have. Thank you.
Thank you, Rodrigo. We do have a few questions to address. The first is from Paul Lapointe. What impact does exposure censoring play on, and how can it be detected? So what impact does censoring have, and can you see the censoring in the analysis? He's got an example here. If a vertical face is 30 meters long, it is not possible to quantify spacings greater than 30 meters. But it may also be difficult to quantify spacings that are 15 meters. Also, if only fractures that are greater than some threshold, say 2 meters, are recorded, how does this impact the calculation?
Yeah, well, obviously it is impact, and obviously when you go to do the analysis and use the normalized correlation count in, for example, in your scan line, you want always to be able to see the smallest fractures that possible. So we usually use the hand lens, and we try to measure as much fractures as we can to get this the censoring and the truncation effect out of the way as much as it is possible. But yeah, there will be always a size of fracture that you will not be able to see. But that hasn't been directly analyzed the impact of that in the method. But you can see that, like, from this plot here in the Pedernales State Park, for example, we are able to go through very wide size of spacing. So like from 1 millimeter to all the way to 10 meters. So that gives us some confidence that and that gives us a pretty nice slope that we can adjust with a power law. So that gives us some confidence that we are seeing the real data, not really some censoring or effects. But when you go maybe to the end of this plot, that may be affected by some of these effects that you just called attention to. But overall, the method is quite, I'm quite confident in using this with the field data, yeah.
And a second question from Paul. Because spacings are ill-defined when fractures are not subparallel, how is this taken into account?
Okay, yeah. So, well, we always try to do our scan lines as much as perpendicular to the fracture set, and we always try to analyze one fracture set per time, and that will give us, like, it is easier to do it that way, because you can imagine, like, if you have different fracture sets going in different directions and you're trying to analyze to do a scan line optimized by optimized is going to be basically impossible, right? So we choose one fracture set that we want to analyze the arrangement, and we do a scan line trace that is as much perpendicular to that one as possible, and we go from there. But in case that we cannot do that, for example, in the case of image logs, for example, sometimes you just have to work with what you got, right? And it may be not the perfect perpendicular scan line going through the well trajectory, and then you would ideally have to correct that using Terzagh correction and use the corrected spacings as the input for the normalized correlation count. Yeah, but ideally you want always to do your scan lines perpendicular and acquire the with the less error possible, right?
A question from Gary Prost. Are the fracture measurements always on a single bedding plane in the studies you've done, or do they cross bedding and units? If they do cross bedding and units, do you see an effect of different bedding thicknesses and composition on the fracture clustering?
Yeah, so we always do this work trying to get to get away from the other variables that can change the spatial arrangement, right? Because you can imagine that if you have fractures that are within a bed, and obviously the bed thickness will have impact on how wide the spacing are in this fracturing. So if you cross a bedding, instead of seeing the spatial arrangement of that set in that bed, you will just see that the spatial arrangement just changed when you cross that bedding interface, right? And that's not exactly what well, at least not what I'm looking for when I try to analyze the spatial arrangement of the fractures. I try to really keep the analysis on the same pavement, on the same bed, with the same fracture set, and try to get rid of all the other variables that could be changing the distribution of the fractures, and to be able to really analyze what is happening to that fracture set in that location. And for that, we really have to think where to put the scan line before that. And obviously, as I said before, sometimes you you can't choose if you have a well, but then you just have to be aware that if you're crossing beds, yeah, you may have a substantial change in your spatial arrangement, and you need to be aware of that and do the corrections, subdivide your scan line, for example, and make separated analysis for whatever objective you want to do. You want that. So, yeah.
Next question is from Everton Rodriguez. Can we adapt this workflow for faults and fractures identified in high-resolution seismic data?
Yeah, well, for sure, like, I'm not sure if you mean the 1D or 2D analysis, but for sure, like if you have some well data that goes through fractures and faults, I mean, the technique analyzes basically distances between features, right? So if you want to analyze opening mode fractures, shear fractures, faults, as long as you have the positions of them along a trace, you can use the NCC 1D. And the NCC 2D, we're still developing it, but if you have a map with the traces of your faults and you want to see how the barycenter arrangement is changing in there from one place to another, yeah, obviously you can calculate that from seismic. If you have your planes, your traces from seismic, you could easily put it in a GIS software, calculate the barycenters, and if you have the X and Y coordinates of these barycenters, you could use it as an input to analyze using the NCC 2D. And this is actually a good approach to see the spatial arrangements of different places in your seismic, if that's what you're looking for.
Next question from Leno Gomez. Can you please explain why NCC and NCC 2D provided two different cluster widths 8 versus 19 meters in the Marble Falls outcrop?
Yeah, sure. Well, Leonel, actually, Leonel is one of the experts, and I'm very happy that he's here today. And well, my answer is that probably we are measuring different things. In the 1D analysis, in this scan line, we analyzed these fractures that are east-west, and these are veins, right? Northwest, maybe here. And these are all veins. But in the 2D analysis, I mapped all the fractures and also joints, probably joints that are here in the middle. So at the time, I was not trying to do this comparison between the 1D analysis and the 2D analysis, and that's why they are different. But if a comparison was ever to be done, I would have to go back to these drawn images here, for example, and remap it only the same sets that were described in the 1D analysis, in this analysis here. In this case, the east-west veins, and map all these traces from the east-west veins, and then recalculate the barycenters and recalculate the NCC2D. And then I would be able to really make a comparison and think about the differences. But this is on plans for future works.
Great. The next question is from Vincent Hisekers. Any thoughts on pushing the development to 3D? This would allow us to connect spatial arrangement to subsurface 3D DFN modeling. And following question, how does sample size affect the NCC analysis?
Yeah, so this is an interesting question. Yes, the method is we're expanding it to 2D now, and obviously the 3D is always on the next step, right? You're trying to always be able to analyze the whole geometry, so 3D will be the perfect approach for that. And yes, on the DFN comment, I would like to really make a point in there that basically most of the DFN tools that we have, for example, if you take Petrel to do a DFN model, the internal organization of the DFN is always going to be random because it's based on a Poisson point process that is random. So when you are able to analyze a fracture map, a fracture trace map, or a scan line, and you're able to actually characterize the fractal dimension of that, or you're able to characterize the spatial arrangement of that, and if obviously even better if it's in 3D. The next step, once we do that, would be to create a DFN tool that can incorporate this spatial arrangement in the internal distribution of the fracture planes, because it's not there yet. But this will be the best approach to have to really improve the DFN tools that we have today. But yeah, we're still working on the 2D version of that, and hopefully in some time we'll have nice results to share with you, and hopefully go towards the 3D.
And the second question from Vincent was, how does sample size affect the NCC analysis? And do I need to sample at least 2 clusters to get a statistically meaningful result?
No, we can analyze, we can use NCC with different sizes of different numbers of fractures. For example, in this analysis here, we have 916 fractures. This is a very, very densely rich in information. This scan line is very rich in information. They have 916 fractures. But I have shown you some other examples here. For example, this one has 260, which is almost a fifth of the number of fractures of the other one, and this one has 109 fractures. So although we have very different sizes of number of fractures, I was still able to see the spatial arrangement of all of those scan lines, and that's basically what you need. Like you need to go through your data, have enough data. Obviously, if you have too much to fill, like I would say, like if you have 10 fractures, probably you will not see much. But as long as you have like 100, something like that, you'll probably see a signal there, and we're going to be able to analyze the spatial arrangement of this technique. Yeah.
Next question from Ibrahim Simin. Have you considered the effect of mineralogical and grain size variation in fracture clusters in the frontier sandstone along the strike of your scan line?
Yeah, this is basically this is of course the reasons of clustering may change, and the clustering may arise by different processes, right? And this technique here doesn't tell you why the cluster is there. It just quantifies how much of the clustering is there and how wide it is, right? But for sure that all these mechanical compositions, bad thickness, the presence of localized structure like a fault, uh, folding, all these, the burial history, the 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 content of synchromatic cement, this all of this could also impact how much of clustering you have in a fracture set. And but this is a very complex topic, and I'm also touching on that on my PhD. I'm also studying the impact of diagenesis and in forming this type of clustering, the synchromatic cementation specifically. But along with this, all these causes, there can be many causes. So yeah, of course, that I didn't analyze the changing in the size of the grains, specifically causing clustering in the frontier formation. But I bet that this is obviously major factor changing the fracture behavior in there. And if it changes, NCC is obviously also able to identify where it is changing and the size of the clustering in there. But you will have to make some other analysis to be able to really tell that the grain size is what is causing the clustering.
Wayne Nar has, I think, a related question. We might guess that some clustering is initiated by minor faulting, whereas other times it is more due to the lithology, and other times it may be stratigraphic. Do you have any reason to expect that the correlation count analysis will help us understand the root cause of the clustering?
Yeah, well, this is a good question. The correlation count will give you basically the size and the spacing of the clustering, and will give you how much of that clustering is, if it's is distinguished or not from random arrangements, right? And if obviously, I don't think that only with correlation count you will be able to distinguish the reasons of each clustering along your scan line. But I think that if you use some other tools or analysis, and together with the NCC, you could probably be able to separate these clusters in types. For example, maybe you have a cluster along in your scan line that is a clustering that is not distinguishable from random. It's a random clustering. And this is a quite weak clustering that may be different from a cluster caused by faults that is expected to be more maybe localized along your scan line. So if you do the analysis along with some other information, obviously you will need to see like where is the fault at, right? And you may be able to differentiate between these clusters using NCC as well. But I think that the integration of all the information that you would have in subsurface would be the key to using NCC as well, would be the key to really have a deeper understanding and be able to separate all these different clusterings that you may have. Yeah. Any other question? Any other question?
Yeah, we have two more. I think they're relatively short. Is it possible to analyze topographic lineaments using the core count program?
Yeah, well, yeah, you for lineaments, you would have to have a map. Well, you will basically map your lineaments on your topographic map, and then you will do a scan line through your topographic lineaments to be able to analyze that in the NCC. So you basically you'll have to input in NCC the intersections of your scan line with your lineaments, your topographic lineaments, and as long as you have the position of these lineaments along the scan line, you could input NCC in the NCC. So basically what you need is the position of your lineaments and along the scan line trace. And this is really a good point because you don't need to be analyzing only fractures in the scan line, fractures in the outcrop that you analyzed doing scan line, very detailed scan line, looking at the outcrop. You could also use in wells, you could also use to analyze traces in satellite images or magnetometry images and other input data, as long as you have distribution of features along a line. You could use NCC to analyze the spatial arrangement of these features and help you to interpret that.
And a question from Orlando Ortega. In the frontier formation example, you hinted at the cementation as a potential control on fracture clustering. Do you think that more cementation increases or decreases clustering?
So this is a very this is a very good question. So the thing with the cementation is also obviously the amount of cementation that you have in the fracture, but not only the amount of cementation, also the strength of your cement, right? Because if you think about reactivation of the fracture and widening of fracture as the strain increases in your reservoir, if you have a weak cement in your fracture, this cement will tend to break many times, and the fracture will tend to widen and widen and widen, forming, for example, crack seals coaxial structures as the deformation goes, right? And then instead of forming new fractures on the sides of this fracture, you would concentrate the deformation on the same fracture always, right? Because it has a weak cement, or it has a low proportion of cementation that makes that fracture really prone to reactivation. On the other side, if you had a fracture that is cemented by a really strong cement that is not going to break and it has a really high strength, instead of recracking that same fracture, you will have to create a new fracture on the side as the strain accumulates on your host rock. So you will end up forming you will end up having a process called the crack jump process that was published by Caputo and Hancock in 1999, I think. And this is actually a process that is the crack, instead of recracking the same fracture, because you have such a strong cement, it will form a different fracture on the side, and it will keep forming different fractures every time the strain gets to that threshold. So this kind of process could give you clustering. And in this specific hypothetical situation that I'm giving you now, this could be an example of how the cement is causing clustering of fractures. But we all know that along with cement, we also have differences in strain along the reservoir. We also have differences in mechanical behavior. Host rock itself can change its mechanical behavior depending on the depth, right? So there are so many variables that should be analyzed that the problem is not that easy to solve. And it is more like a very complex problem that needs to take into account, like the temperature needs to take into account the chemical solubility of these minerals, the pressure, and also the fluid flow part needs to be taken into account to be able to really address all these variables and to predict if the cluster will be there or not, right? So yeah, fracture cement is part of the problem, and that's what I'm studying here now, and hopefully I'll be able to give maybe a new talk with some results of this in the coming years.
Great. Rodrigo, if you have time for one more question, one just came in a moment ago.
Yes, sure.
Yeah, can you comment on the data preparation from the subsurface well image log to overcome the short intersection distance in vertical wells of formations or rock types?
Yeah, well, in this subsurface image log that I showed you, these are horizontal wells, right? So what they did is that they mapped the fractures along these image logs, and with the position of the fracture along the length of the well, and you're able to use that in NCC. And well, you asked about the vertical wells. Of course, that's the problem with the vertical wells, is that you're not going to see the whole picture of the fracture arrangement in subsurface, because it's very hard to intersect a fracture that is vertical in a vertical well. So the problem in that case will be really to have a representative sample of the fracture arrangement of subsurface that would give you a reliable signal to analyze with NCC. That would be my main concern. But as long as you have a reliable data set from subsurface of fracture positions along the well length, you can use NCC and have analysis.
All right, that concludes the Q&A session. A big round of virtual applause to Rodrigo for presenting this to us today. And if you're not watching the chat, Steve Laubach has reminded us that the NCC software is available through the open access Merritt et al. Paper. And I believe there's a GitHub link within that. And we will try to remember to post a link to that GitHub software source when we post the YouTube video for this presentation. Again, thank you for joining us today. The May edition of the PSGD monthly webinar, and we'll see you next year, or next month in June. Thank you.